All right, so we're going to be talking about component vectors, which are a strategy that we can use for organizing the math of projectile motion. We'll be looking at an example problem together. In this example problem, we have a projectile that is shot out of a cannon at 50 meters per second. The cannon is angled 30 degrees above the ground. The two questions we're looking at is how long does it take for the projectile to land and how far away does it land? When we see a problem like this, the very first thing that we want to do is we want to draw a picture to model this problem. So this picture shows the 50 meters per second as the speed at which it's leaving the cannon and the 30-degree angle at which it's shot. Now, in this picture, we want to separate that 50 meters per second into the horizontal and vertical component vectors. So, how much of that speed is going into horizontal motion and how much of that speed is going into vertical motion. So, we can label the horizontal motion as x and the vertical motion as y. And now that we have that set up, we can use trig functions to say that the sine of 30 degrees is y over 50. With a little bit of algebra and our calculator, y is 25 meters per second. So when the projectile leaves the cannon, 25 meters per second is its vertical motion. Similarly, we can use cosine. Cosine of 30 equals x over 50 to find the horizontal. Little bit of algebra and calculator gets us that x is 43.3 meters per second. So its horizontal motion at the moment it leaves the cannon is 43.3 meters per second. So notice we started with this initial 50 meters per second, which was on an angle. And with a little bit of trig, we're able to figure out how much of that motion is horizontal motion and how much of it is vertical motion. Now that we've done that, the next question we want to address is when does it land? And when we're thinking about when it lands, we are only going to be looking at the y motion because the horizontal motion does not affect when it lands. What affects when it lands is gravity and gravity pulling it down toward the ground. So it's worthwhile here to pause and ask, what do we know about gravity? We know from our activities in class together that it's a quadratic pattern of change. We know that the acceleration due to gravity is negative 10 meters per second squared. Negative because gravity pulls us toward the ground, and our positive motion from our projectile is away from the ground. So we use negative for the opposite direction. And the equation that we found to model how high above the ground it is if it started from the ground is h equals 1/2 acceleration times time squared plus the initial velocity times the time. Knowing that negative 10 is the acceleration due to gravity, we can then translate this equation into h equals negative 5t squared plus vt. Bringing that back to our question of when does it land, we've got h equals negative 5t squared plus vt. And our initial vertical velocity is the 25 meters per second that we found earlier. And when it lands, that's when it hits the ground, its height above the ground is 0. So we're going to change h into 0. So the equation now is 0 equals negative 5t squared plus 25t. We can solve that by factoring. Factoring out a 5t, 0 equals 5t times negative t plus 5. And then if we have two things that multiply to 0, it must be the case that one of those two things is 0. So either 5t is 0 or negative t plus 5 is 0. That tells us that t is 0 or t equals 5. T equals 0 was when it shot out of the cannon at the beginning. So while it is true that it was 0 at t equals 0, that's not actually useful for us for the question of when does it hit the ground. So our answer for when it hits the ground is t equals 5. It lands after 5 seconds. Now that we know that, we're able to answer the question, how far away does it land? And when we're thinking about how far away it lands, we're only thinking about the horizontal motion because how high above the ground it is does not affect how far it's going. We've got the equation d equals rt because it doesn't have any acceleration we need to worry about. It's just a simple distance, rate, time problem. The rate is the 43.3 meters per second that we found for x, and the time is the 5 seconds that we just found for when it hits the ground, because when it hits the ground is when it stops moving. So then we know that the distance is 216.5 meters, and so it lands 216.5 meters away. So to summarize, when you see a problem like this, you start by drawing a picture. The total velocity is the hypotenuse of a right triangle. You can use trig functions to find the x and y component vectors. Use the y component vector and the gravity equation to find how long it takes to land. And use the x component vector and the time in motion to find how far away it lands.